Hi, welcome back for the first 2017 paper. You must have finished up to question number 13, and now we're going to start with the question number 14. Let's just go all the way to question number 14. So again, I'm hoping that you've already paused or you've already solved this question number 14 yourself, and now let's try and work it together. So this one is asking some liquids conduct electricity. This property can be used to pump liquids through the pipes. Fine. So now short section of rectangular pipe. So this is a rectangular pipe. So you have a current going in. The magnetic field is here. Add an arrow to show the direction in which the liquid will move. So just use your left hand rule. Magnetic field is, so you have to find the force. Magnetic field is this finger, so it's upwards. Current is in this direction, so as you can see, the arrow is coming out of the page. So just draw it like this. So that would be your force. So left hand rule. All right, let's do the next one. A practical demonstration of this principle is used to rectangular electrodes. So you have two rectangular electrodes, that's fine. Each other on the other side, a distance of 0.6 mm. So this is the length that the current has to travel. So the length is 0.6 10 to the power minus 3 millimeters to meters. That's this. Now the dimensions are shown in the diagram. So this is the width, and then if I use this, so this is the area through which the current is traveling. So I can calculate the area, which is 28 times 10 to the power minus 3, converting to meters. And sorry, the width is 0.5 10 to the power minus 3. So multiply them and get the area, and then using R equals resistivity times length divided by area, calculate the resistance. Resistivity is also given here. So if I just plug in all the values and then use your calculator to figure out the right answer, I am just going to take the answer. So this is plugging the length here and the area. So I get my resistance as 68.6 ohms. I got the resistance now, and I have the voltage as 1.5. Now let's show the current. Current is voltage divided by resistance, potential difference divided by resistance, and this is 1.5 divided by 68.6. So if you use your calculator, it's giving something around 22 milliamps. It'll give you some 0.00, so you convert it into milli, and that's your answer. Now let's move on to the next one. Hence calculate the force on the salt water. Now because there's a current in the salt water, we could just use BIL. You have magnetic field. What was magnetic field? Let's go back. 0.4 times 22, because you have to convert this into milliamps, and then the length was 0.6 10 to the power minus 3, converting the units, because if you do not convert the units properly, again the answers would not be right. So this is giving me somewhere around 5.3 10 to the power minus 4 newtons. Again, an important part, do not forget to write the unit. Pause for the next question. If you've already done it, let's just solve through it. Idea is not focusing on the answers, where we're focusing is on the method. Let's just read through the question. So you have a battery which is 5 volts, fine, 100 ohm resistor, and an uncharged capacitor. Now because the capacitor is uncharged initially, what would happen? The entire voltage will be across 100 ohms. Slowly the capacitor would start charging up, and once the capacitor is fully charged, all the voltage will be across the capacitor. That's what it's asking you to explain. The first point, all 5 volts appear across resistor, that is important, and capacitor has no voltage because it is uncharged, hence no potential difference. Now the second point, slowly the voltage across capacitor increases. I don't write slowly because it's quite quickly. So the capacitor starts getting charged as capacitor charges. So charges, potential difference across capacitor increases. Okay, and as capacitor gets fully charged, so your capacitor is fully charged, so all the potential difference, so 5 volt, will appear across the capacitor. So your capacitor is now charged, and so hence the potential difference across resistor would become 0. Okay, and across resistor would become 0. You could, if this is higher mark question, you could talk about the time constant. Let's see the time constant. So the time constant is R 100 times the capacitor 50, which is micro, so it is 5000 microseconds, or if I convert this into 5 milliseconds, yeah, 5 milliseconds. So in 5 milliseconds, so approximately in 5 time constants, the capacitors would get almost fully charged. So around in 25 milliseconds, so you could write that in 25 milliseconds, the capacitor gets almost the entire voltage across it. B. The battery and switch are replaced by a signal generator. Fine. The signal generator has negligible internal resistance. That means all the voltage across of the signal generator will be available to the circuit. The graph shows the square wave output of the signal generator. So that's my square wave. The frequency of the square wave is 20 Hertz. Now let's just understand what's happening here. The square wave is changing its value. Here the voltage is peaked up. So when the voltage is peaked up, your capacitor would charge. And the minute the voltage is 0, the capacitor would discharge. So your capacitor, instead of constantly charging, would charge and then discharge, charge and then discharge. This would happen across the capacitor. Now what we're going to do is, what we have to be like accurate because they has given you the values. So I'm going to find out the time period of this square wave. So frequency is 1 over t, calculating time period, which is 1 over 20, which is 0.05. Is that right? Yes. So if I convert this into milliseconds, because I calculated the time constant in the previous question as 5 milliseconds, isn't it? The capacitor charging, the time constant of capacitor. So this will give me 50 milliseconds. All right. So first thing I'm going to do is see where is my these time constant, because it's also asking you on the graph add values to the time axis. So I'm going to add the values to the time axis. So let's say I'm considering my cycle starting from here. So one cycle ends here, because always remember your cycle should start and end at the same point. So if I'm taking one cycle here, so the second cycle should start from here and end here. So see, blue one and the red one. Blue is the first cycle and this is the second cycle. So I'm going to add here, this would be my 50 milliseconds and this would be 100 milliseconds. Done. First part of the question done. Now sketch a graph of the potential difference across the capacitor for 2 cycles. Now we know this is going to charge up to this point and then going to start discharging. But would it reach the maximum voltage of 5 volts? That's the question. Because see the 5 volts, if I draw it like this, I don't know yet if would it be completely charged in that point in time or not. So what I'm going to do is I'm going to figure out using the time constant, whether it would be reaching to a 5-volt value or not. So let's just see what is the time constant. The time constant is 5 milliseconds. So almost to reach its peak value, almost, not 100%, almost to reach its peak value, how much do I need? I need around 5 time constants. So 5 times 5 milliseconds, that is 25 milliseconds. So in the half cycle, that is 25 milliseconds, my capacitor would be almost reaching up to 25. So I'm going to use a different color to make it clear. Let's use red. Come on. Okay, this is taking too much time. Let's just go already. Okay. So from here to almost here. So even if you go up to the 5, it'll be all right, but it can't be missing too much of it. And then obviously if it's charging in 25 milliseconds, it'll be almost discharged to 0 in the next 5 milliseconds. So that, remember, the shape has to be exponential for charging and exponential for discharging. Again, charges all the way up to 5 and discharges. That's it, done. Yeah, we get it. So first, it's a very kind of like AO3 kind of question. You need to be able to link the time constant of your charging circuit to the time of your square wave pulse, to the time of the signal generator. Okay, pause, do it again. If you are not happy, replay the video, but do not move ahead to the next question till you get it. Okay, all right, let's just go for the next one then. 16th, the neutral lambda particle is a baryon of mass this much, contains one strange quark. The table shows quark and the relative charge, the quark content of this. So the quark content is UDS, which is 2 over 3 minus 1 over 3 minus 1 over 3 is 0, hence a neutral lambda particle. Justified. Easy. These questions are very easy. They're always asking you conservation of charge, conservation of baryon number, conservation of momentum. Whether do you understand they move in a magnetic field? Why would a particle move in a magnetic field? Because it would have a charge. Okay, so it's just similar kind of questions. Okay, let's just stop and move. Calculate the mass of this particle in kg. Do we have the mass here? Okay, so they have given you the mass in this unit and they're asking you to convert it into kg. Very simple. Just get rid of all the things. So first I'm getting rid of million. How do you get rid of million? By timesing it 10 to the power 6. Then I get rid of electron volts. How? By timesing it with the charge of an electron, which is in your data sheet. Then I get rid of the c square in the denominator by plugging in the value of the speed of light, 3 times 10 to the power 8 squared. That's it. So you just plug in all the values of the things that are given. Slowly remove all the extra unknown required units, and that's it. Do not learn the formula. So the answer, I'm just going to write the answer here. 2 times 10 to the power minus 27 kg is already given. We're getting rid of the units. All right, let's just do the next one. Our students suggest 5 ways this particle might decay. These are these. Okay. Suggest which of these decays are not possible. Okay, deduce. Okay, so you're not only telling which is not possible, you're also giving a reason, because of 6 marks, they're at least looking for 3. So I'm going to just quickly see which might is not possible. This one is clearly charge is conserved is possible. So what about this one? Is this possible? It is a lambda particle decaying into sorry, so your neutral particle is decaying. Wait, my screen just froze. Okay, so now this, and I'm going to think of this thing, is this possible. This is absolutely not possible. Why? Because if you have one single particle, momentum would never be conserved. So for momentum to be conserved, it should have two particles. So at least, okay, we got one, this one. So I'm going to just number them. 1, 2, 3, 4, and 5. Now also, if you see the last one, that is also not possible. Why would that not be possible? Because the charge is not conserved. Clearly, if the charge is not conserved, that's not happening. So this is also not possible. Now, so we're going to write the full fifth point, that because the charge is not conserved, this is not possible. Now let's try another one. What is happening to, let's see, the third one. What do you think is happening here? In the third one, we are not able to, is the charge conserved? Yes, the charge is conserved. What about then, think about the barrier number. Is that conserved? If I see the barrier number, all right, so the barrier number seems to be conserved because you'll have +1 for neutron and 0 for pi particle. So this is conserved. Lepton number is conserved. So third is possible. Let's do the second one then. The charge looks to be conserved, plus and minus, so conserved. But what about the barrier number? See, the barrier number is not conserved. So this why the second one is not possible. Second, the barrier number is not conserved, hence not possible. Let's see the first one. Is that possible? Charge is 0 on left, 1 and -1, conserved. Barrier number 1 on the left, 1 on the right, conserved. And so yes, so first is possible, second not possible, third possible, fourth not possible because momentum is not conserved. Fifth, you have not possible because clearly the charge is not conserved. That's it. Okay, let's just move on to the next one then. Lambda particles were first detected in experiments which made use of cosmic rays entering the atmosphere. How the cosmic rays could lead to creation of a lambda particle. So energy, how does energy convert into a particle? So how does energy conserve? So using your Einstein's relation, energy can be converted into mass using this. That's it. So how does a cosmic ray possibly get converted into a particle? By Einstein's energy equation. Energy can be converted into mass using this equation. Okay, let's do the next one then. This cannot be directly observed. Why? Because why you can't observe? Because it's a neutral particle. Remember, we observe the particles by their path in the magnetic field. Because it is neutral, it would not form any kind of track, any kind of path. No charge on the particle. No charge means no track. Okay, remember, you see all those tracks in the magnetic field moving here or here. So these tracks happen because the particles would have charged particles. But when it breaks up into different particles as seen. Remember, I always keep on telling you these subparts, they act like a scaffolding to the following parts. So this first part here tells you that this particle breaks up into the different particles. So if I see that third is possible, so how do I detect this particle? Because of this and this. And how do I detect these two? These two are also neutral. How do I detect? Because of the conservation laws. Okay, so how do I detect? Is by laws of conservation. Whose conservation? We are conserving laws of momentum to find our conservation of energy, and also the decay particles attract. Sometimes the decay particle can also have a track. So to track of decay particles, say track of decay particles to tell that this particular particle exists. It has come from some other particles. All right, let's do the next one then. A student investigates the motion of a friction-free trolley. Fine. Okay, so this is the gada. Okay, fine. So now, let's just see what is information that is important to us. Why they have given you this? Just underline this. We might need it in the ahead questions. Now the two ends of the wire are connected to 1.5 volts. So this entire wire is connected to a 1.5 volt battery, and this particular thing has a metal ring about it. So now this, see, so this is this part, okay, and then if I use a different color, I can show you the next part. So if this is, okay, I cannot choose the next color. So this is my second part and this is my second part here. Okay, all right, let's just see. So have you understood the circuit? So what's going on here is they have applied the voltage across AB. This is 1.5 volt, and wherever is this point going, this head is going, that part is basically increasing the length of the circuit that is available, and then that would change because the length is changing. So see, can you see this is kind of acting like a potential divider circuit? So this length is increasing, and because the length is increasing, the resistance would change. And I think this is what is going to ask. Let me just explain how the potential difference will vary as the loop moves along the length of the wire AB. So yes, so how would this potential difference change? Now think, what's happening? Is the length changing? Who is changing the length? The length is being changed because of this small loop at the top, and this change of length is causing the change of resistance, and hence there will be a change in the potential difference. So we'll just start the first one. What is when the car is here? What's the potential difference? 0. At the start, at A, the potential difference will be 0. You can also write that this is acting like potential difference circuit. So that would, the minute you write, the examiner understands, okay, fine, this is going in the right direction. Okay, so we got the potential difference. So as the loop moves, what's happening? The length is increasing, length increases, because of which resistance increases. You could write resistance is rho L over A, not necessary though, because you've realized that resistance is increasing because the length is increasing, and then as, so V is proportional to resistance, so V increases. That's about it. This part, the length is increasing as your loop moves, the length is increasing. I come here, so the length is increasing. As the length increases, resistance increases, hence the potential difference across that part of the length increases. Just a simple potential divider circuit. Let's see, the graph shows the data obtained from the data logger at different time. Potential difference is this much. Yeah, so as the time, so see what we just derived, that's given here. As the time increases, the potential difference is increasing. Determine the velocity of the trolley at 1.5 seconds. Now 1.5 volts shows 2 meters. So at 1.5 volts is 2 meters. I'm just going to see at 1.5 seconds. So this might not be accurate because I am not using a ruler. So it is 0.6, 0.7, 0.65, 0.75, 0.8. So just counting, it is, I think, giving me 0.9. What is this exact? Yeah. So or what it, say, is that the right way? No, that's not the right way because it's not a straight line graph. So what I'm going to do is I'll have to draw a tangent here. Okay, so let's just bear with me. This is, okay, sorry, this is not coming a straight line. Let's just try and make it a straight line. Don't know why my computer is acting so slow today. Come on. Okay, so let's just do. Wait, come on. Done. Okay, so we are just going to draw a straight line here. So just draw a straight line, and then then complete the triangle. So I'm going to just take this triangle from 2 to 1 second. So I have exactly midpoint here, 1.1, and this one is point, let's just, is it coming to, okay, this one is 1.1 minus 0.2 divided by 2 minus 1, that is 0.9. So 0.9, I have the gradient as 0.9 volts per second. Now I'm going to tell you a trick kind of thing here. So now it's asking me velocity. What's the unit of velocity? It is meters per second. This, if you don't understand, if you understand, you know, you've got the gradient and you convert the gradient into meters here and then you calculate. Or you can use this. The velocity is in meters per second. I need to convert this volts into meters now. How do I convert volts into meters? 1.5 volts is 2 meters. So how much would be 0.9 volts? If 1.15 volts is 2 meters, 0.9 volts will be 2 divided by 1.5 times 0.9. That's it. That's it. That's your answer. So what we do is, because it's a curved graph, calculate the gradient. Do not read from the graph. I started it so that we need to understand what mistake we are doing. Never calculate the reading from the graph. If it's a curved graph, always calculate the gradient. Now you will have to use your physics and maths to figure out what they're asking. Now this one is not pure physics question. Do we get it? So now this just gives us the speed. If we wanted 3 threes after, if I was a point, I'm getting 1.2 meters per second. That would be my speed. Let's just do this one. The student calculated the velocity at 2 to be 1.5. Determine, so we calculated the velocity at 1.5 to be 1.2. So we got at, just writing, you know, sometimes it can be so confusing, all the data. So just write again. We calculated the velocity as 1.2 meters per second. Then at 2 seconds, this one gives us the velocity as 1.5 meters per second. All right. Now, what is acceleration? Acceleration is change of velocity over change in time. The change of velocity is 0.3 in 0.5 seconds. So that is 0.6 meters per second squared. So we got the acceleration. Now what it is asking, whether the student's measurement of theta was within uncertainty period. Now let's see. What is the formula for acceleration on a frictionless incline? 9.81 sine theta. So I got my acceleration as 0.6 divided by 9.81 will give me my sine theta. So use your calculator and see what sine theta is coming. Do not see from the mark scheme. Use your calculator, okay? Because sometimes you'll be surprised. You are not converting radians to degrees. So you should have that practice before the exam. You don't want to go into the exam not knowing what setting is your calculator on. So if I'm using this on my calculator, I'm getting around 3.6 degrees. Whereas if you go back into the question said 4 degrees with an uncertainty of plus and minus 1. That is a 3 degree to 5 degrees. Brilliant. It falls into the range. So yes, it is within the uncertainty quoted. All right, let's do the last one. It is last one, isn't it? It should be. Are you lost? Are you lost? Oh yes, it is lost. Let's do the 18th one then. A motor usually have a rotating component which can do work. Fine. A motor lifts a load in time t. So this is the load which is being lifted in time t. The axle of the motor has a radius r and a force F. The power produced by the motor can be calculated using this. Derive this using this. Okay, not tough. Let's start. So I have power, which is work over time. I'm going to directly go for the formula for work, which is force times distance divided by time. Now, the distance this load moves in a time t is nothing but the speed. So force times velocity. Now, I want moment and I want angular velocity. So I'm going to convert this velocity into angular velocity. So my F is, force is radius times angular velocity, omega. So V is r omega, radius times angular velocity, equation sheet again. Now, what is force times r? See, this is the force, line of action of force, and this is radius. So what is force times perpendicular distance? It is moment. So moment times angular velocity. That's it. Always so there was a little bit of thinking required here when you were writing distance divided by time as velocity, and then another thinking required when it is force times r should be angular moment. That's why it's 4-mark question. You can't have everything in the equation sheet now, can you? All right, let's start this one. The electrostatic motor was first demonstrated by Mr. Franklin in 1750. The diagram shows a simplified version. Consists of a rod with oppositely charged. So you have a positive, which is getting attracted here, and this negative, which is getting attracted here. So it is producing force, and because it's a pivot, it will end up producing, so I'm taking this as R, it'll end up producing a moment. This produces a clockwise moment, and this is also producing a clockwise moment. Fine, let's continue. In the diagram below shows electric field lines. Add to the diagram the direction of the field lines. Now these are AO1 questions. You cannot make them wrong. This has to be done. Where does electric field start from? Electric field line starts from positive. So add the arrow. Don't be stingy. Yeah, go ahead. Add arrows to all possible lines. Where does it end? It ends a negative. So these arrows should be going downwards. They start from positive. These arrows should be starting from the positive. Voila, 3 marks done. Okay, next to the next one. The distance between the centers of each charged pair is 5. Show that the force between this pair of charged pairs is 0.04 and the charge on each pair is this. Equation sheet, force between two charges, K, Q1, Q2 over R squared. Value of K comes from your equation sheet. Charge is 0.1. Because it's in micro, 10 to the power minus 6. Same, the other charge is also same. Minus 6 divided by distance is 5 times 10 to the power minus 2. The whole squared. Remember, R is in centimeters. So you need to convert. Charge is in micro. You need to convert. Any mistake, you're not getting the right answer. So plugging your K, 8.99 times 10 to the power 9 and times all of this. Use your calculator. My answer is 0.036 Newton, which is very close to 0.04 Newtons. Okay, next to the next one. The table shows the typical power and the corresponding angular velocity. Okay, electric car requires this much power, this much angular velocity. Vacuum cleaner requires this much power and this much angular velocity. Small pond pump requires this much power and this much angular velocity. You deduce which of these is possible. You should use the word equation in A and assume the length of the rod in the electrostatic motor is 8 centimeters. So I'm just going to go back here. So what's going to happen? What's happening here? So you have a force acting. What is the moment produced? This length is 8 centimeter. So my R is 4 centimeter. The total moment would be F times R plus F times R. So times 2. Why? Because both of them are in clockwise. This charge is also getting attracted, produces a moment. This is also getting attracted, produces another moment. That's why times 2. We got this as 0.036 times radius is 4 times 10 to the power minus 2 times 2. So this gives me the total moment. So I'm just going to use the calculator. This gives me a total moment of around 2.89 10 to the power minus 3. That's my moment. Okay, I got the moment. Now the power. Okay, now how do I get the power? So just times it with the angular velocity, because it's a small moment. So okay, you know what we'll do. Okay, here. So I'm going to just check for the pond pump first, because realistically, you know that you have very small moment. So does it give you that power? So I got the moment as 2.89 10 to the power minus 3 times, I'm taking this angular velocity, times 200. So this is giving me around 0.6 watts. Okay, if you just see, this is around 3 times 200, and this goes to 0.6 watts. Okay, let's try another one just to make sure. Okay, to vacuum cleaner, what power is being produced by this moment? So this is 2.89 10 to the power minus 3 times 1000. Okay, let's see what power it is producing. So this is almost 3. So it's only producing what watts? 3 watts. How much does it require? It requires 1400 watts. So can't. So the only possibility here is the pond pump. To get it, do not get confused. Where is the angular velocity? The angular velocity is not given in the question or whatsoever. What you just needed, use this and see if this is giving you this power. Use this, and no other method, no